So, thank you very much for the introduction. I'm very happy to be here today. Can you hear me?
We can hear you.
We are with you very well.
We can hear you.
Wonderful, wonderful. So, very nice introduction. I'm actually in the gas turbine field service team with Venlo, in Venlo with Sulzer. And Ike Chukwumande was my direct line manager until the beginning of this month. So he asked me if I could spare some time to share some of the activities that I do within the company with this group, and I'm really happy to be here. I think for the agenda, the introduction has already been done by Engineer Shegun, so thank you very much. We'll be able to skip that right away. I would like to use this opportunity to try and look for analogies that we can all identify and relate to. I don't want to make it too technical and too boring. I hope I'll be able to make it interesting. And feel free to interrupt me at any time if something is not clear or you have some questions and you'd like further clarification. After the history of gas turbine, I would go on to illustrate how a gas turbine works. I like to use the analogy to a Benson burner to explain a few basic concepts with regards to the different types of flame and operations that we have. Then I will also highlight one aspect that's quite critical, which would be the variable inlet guide vanes used to control the air mass flow into the compressor. You could compare that to, let's say, the choke in a carburetor. Then I would also go on to talk about some of the servo actuated valves, what I typically do when I am in the field in terms of an outage. I will also talk about some of the typical challenges that I face. I mean, technology is evolving. Certain, let's say, operation systems are becoming obsolete. So there are a few challenges in that regard. And I like to also share with you what a successful job completion looks like, or what I like to leave the site with. Then I would also like to talk a little bit about the future trends that I see and some of the resulting tasks that are up ahead. Then finally, I would offer the opportunity to talk or to ask questions, and hopefully I'm able to answer them for you. So, any questions so far? Nope. Okay, then we can move on.
What's ahead?
Wonderful. Like Engineer Shegun already introduced, I was born in Ghana. My father is a Ghanaian, my mother is a German. With 19, I relocated after writing my Edexcel A-level exams in Ghana. And then I came to Stuttgart and I studied electrical engineering. I started my very first job in Austria with Omicron, and finally I ended up after 17 years evolving through different OEMs and joining Sulzer as a field service engineer. Really, it has been a wonderful experience, of course, quite challenging because of a lot of travel. So COVID was really a tough one for all of us to be locked inside or indoors without having the opportunity to perform the tasks you do on site. You'd have to actually fall back to remote systems, which are not always optimal. So that also brought up a few ideas and possibilities that we are currently exploring. So how long have gas turbines been around? Not so long, actually. The first gas turbine is in Switzerland, was built by Asia Brown Boveri, now known as ABB. And it was in Switzerland in 1939, so barely 84 years. And the first gas turbine actually had an output of about 4 megawatts with an efficiency of around about 17.4%. Now, as you can see, let me turn on the pointer. As you can see here on the left-hand side, you have an overview of what this looked like. It was quite primitive with a single combustor. And you had a turbine, a compressor, so your air inlet here through the compressor into the combustor and then back out through the turbine. And this system has actually or these components of the system have been maintained largely. You always have a form of a compressor. It can be a radial compressor, an axial compressor. Then you have the combustion chamber. This can either be a silo or an annular design. And then typically you would have your turbine or turbines, depending on which OEM you're looking at. You can have the sequential combustion turbine, or you can have just a single one. And typically the exhaust heat goes either into a heat recovery steam generator or a boiler, or it goes straight into the environment, depending if you have a steam turbine attached or not. Then there's usually a generator that allows you to convert the electrical energy stored in the fuel used through the breakup to electricity and also to heat. So the heat would be going into the boiler, and the electrical output will be going through the generator into the grid. And you also need some form of a starting device. So this is how a gas turbine is mainly made up. Now, this first gas turbine was commissioned, quote unquote, by Professor Aurel Stobola, and it remained in service up until 2002. In 2005, Alstom acquired the rights to preserve it, and you can actually visit this turbine in Beer in Switzerland. So if you happen to find yourself in Switzerland, you can actually make a phone call to this number here and see if you can visit the turbine. It's very nice. So this is a cross-section of what a gas turbine looks like, courtesy of Henry Wellman, who was able to provide me with this drawing. You see that you have your compressor here, and your compressor is connected to this is for the V94.2. So for those who don't know what the V94.2 looks like, it's you have two silo combustors on each side of the rotor, and then you have a compressor and then a turbine. So literally there is a startup where the compressor provides pressurized air and cooling air. So the cooling air would be required for the turbine blades and the vanes. And then you will have in the ignition that produces the heat and energy and the combustor, and then the vanes and blades that are cooled to make sure that they do not expand too much, and the heat exhausts into the boiler. You do have bearings that are supporting the rotor. This is a compressor bearing, and that is a turbine bearing. Some of them are sealed. For example, with the Siemens machine, it's sealed. With Alstom machines, you can access them in operation for various tests and adjustments if needed. And just to explain or give you an analogy, I would like now to talk about the Bunsen burner. I mean, some of us will know from Chemistry 101 or our first lab sessions, either in physics. I look back to my chemistry class where we had irreversible reactions of sulfur and ion filings, and we needed a Bunsen burner as a source of heat. And if you paid close attention, you realize that there is a little opening or vent that allows air into the Bunsen burner. And if you start it, you open the valve with the air inlet closed, and you have a yellow flame. This yellow flame is very typical of an incomplete combustion. It means that only the surrounding parts of the gas that come into contact with oxygen are actually burning. And because of that, the flame is cooler than a premix flame. The yellow flame on the left-hand side, which is here, is what we typically call a diffusion flame. It is very stable and very dirty. And what we aim to do with a gas turbine is to adjust a premix flame such that the amount of air to fuel is uniform to ensure we have a complete combustion process going on. And this type of flame actually is very lean in terms of emissions, and also poses some challenges in terms of vibrations within the combustion chamber, depending on the design of the gas turbine. You can watch on YouTube, there are quite a few interesting videos where you hold pipes of different lengths over a Bunsen flame to highlight this issue. And throughout the years, there have been various attempts at trying to get the maximum amount of energy out of the fuel without sacrificing too much on losses in terms of emissions and what have you. And it's quite interesting. This is a simplified, let's say, overview of how a gas turbine works, but you can have different systems. For example, the two-stage combustion, where you would have two pipes. So you would have a pilot flame, which looks yellow in the middle of a blue flame. And if you are able to adjust the unit correctly, you would be able to circumnavigate the critical speeds of the gas turbine during startup all the way to base load. Now, this is the analogy. I want to show you what the concept looks like. So this is a simplified overview of what the gas turbine control philosophy looks like. You have inputs that are communicated to, let's say, a central control room or a main control room. I think those familiar with the KKS system would know this as the UBA building, where all the cables coming from the field, measuring speed, temperature, electrical output, the temperature of your gas, if you are running on gas or oil, all these commands are coming in also from your boiler. And depending on the control, like whether it's a PI controller or a PID controller, you would have either open loop systems or closed loop systems. In this case, you can operate the IGV either in a closed loop, where you're taking the exhaust temperature as an input, let's say, measurement, which you want to maintain, or you could actually open it over a step controller, literally an open loop. For example, you might want to open the IGVs when you perform something you would call a compressor wash. If your compressor starts to foul, it means the performance is decreasing. You have a lot of dirt and debris sticking onto the blades, and then you typically go through a process where detergent is injected in, and you'd need to open or position the inlet guide vanes such that you'll be able to ingress to the last stage of the compressor. So the first stage is typically known as the variable inlet guide vane. Actually, this concept is not too old. The first gas turbines built in 1975, for example, did not have any inlet guide vane. It means during startup, you just had a screen to prevent birds from being sucked into the compressor, and then the air went straight in through, and then you had the combustion process. So it was just the valves that were being used. Now you have, in addition to the first stage variable inlet guide vanes, you would have usually two variable guide vanes, which are controlled in tandem with the IGV. Now, the reason for doing this is you want the air mass flow through your compressor to have a very uniform swell, so that when you get to the burners and you mix them with the fuel, you have as complete a combustion as possible. This is the underlying, let's say, idea with this control layout. Now, to give you an idea what it looks like, right now you have, this would be what you would see on your HMI, which is your human machine interface. In this case, it's a T3000 system. You could have TXP, you could have from ABB, the Elektro system. So you have an angle that you have to set. So typically when I go to site and there is an outage, the machine is opened up, the linkages are broken. And when I get to site and I'm about to start, I have to make sure that all the linkages are connected again. I have to take a protractor. I need to measure the angle, confirm whether the reading in the DCS matches the reading physically on the machine. And when that is done, I move on to the control valves, and I do the same thing just to make sure that when I command a certain value to the valves or the inlet guide vanes, I am confident that the angle I expect to receive is also driven to. Now, there is a document on which you record all these settings. So, as I said, you have some machines that are so old, you don't even have an IGV. On other machines, you would have only one, and on others, you would have also the VGVs. So typically, I would always have to refer to the mechanical drawings of the machine to be able to know the design angles of operation, and then I'll record them in there, make sure that the limit switches are set, because you need to have a way to control your vane. You have a starting position, and then you have an end position, and you need to have a backup in case your position measurement fails or your limit switches fail. Then you would have what you call a torque switch. And then the torque switch would usually prevent the IGV from opening further. Now, you do have also an overview here for the control valve setup. You see in this case, there is the gas supply coming in here. There is something we call the ESV, which is the short form for an emergency shuttle valve. Now, after your emergency shuttle valve, you would have two strands. One, which is known as your premix gas supply line, going to a control valve. Now, if you are familiar with these symbols, this is a control valve because it looks like the shutoff. It just has an additional diamond on the top, which says you can regulate it. Now, the other strand would be your pilot flame. So in this scenario, if this is your combustion chamber, this would be a classical diffusion flame. That yellow flame, if you are able to look through a side glass into the combustion chamber, you would see a very yellow flame whenever you're in diffusion operation. And from this side, you will see a bluish flame. Now, because depending on the type of burner, you might not be able, if it's a silo, you can look from the bottom, but if it is an annular combustor, you will not be able to see it. You just need to rely on the flame scanners or the flame monitors. And if you look at it, you would see the yellow flame in the middle of the burner and the blue flame around. And one of the tasks that I have to do is to ensure that during switchover, I do not lose the flame. However, during switchover, I have to be sure I do not exceed emission requirements, because the power plant can get penalized. And when they do, usually it comes with a fine that they have to pay, or they can have their license revoked. Now, I will go on to the next slide, which gives us a view of the valves. So this, for example, is the pilot gas, and the other valve in the background is the control valve for the premix line. And this is how it would look like on the HMI. So after your ESV, you will have your premix control valve and your pilot control valve here. And whenever you shut down and both valves are closed, you realize there is what you call a natural gas unloading valve or a purge valve. Now, this is not too old. Actually, this is one of the norms, I believe, that came in the 80s, because accidents occurred and the design had to be changed, because when you shut down, you have, even though it's a small pipe segment, you have trapped gas in here up to 21 bar, or in this case 39 bar. And if you're unable to vent, it means that you would either need to vent into the machine or break the pipe before, which means that in a scenario where you're performing an outage, you are actually introducing combustible gases into the combustion chamber, which is something you want to avoid, because you just need a spark from a welder or something happening in there, and then you have an explosion once you exceed the lower explosion levels. So After I come to site and these valves are overhauled, sometimes they're taken out for service to a different company, and when they are brought back, I have to make sure that they function the way they did before. In order to do that, I position the valve at a 50% stroke, and then I go from open to close and from close down, sorry, from close to open and from open to close. And in doing so, I try to determine the offset that allows me to have a value that's symmetrical around the 50% stroke command. Once I'm successful with that, I change the gain factor of the valve such that when you have a step response means you give a certain command set point, 10% steps from 0 to 100. So I want to see the valve perform one overswing and no underswing. And on my way down, I expect only one underswing and no overswing. So that would be the gain factor. So in a PID controller setup, your P constant is, in this case, a gain factor. The I would be the integration over the time. We don't have a D because we want to have it quite fast and responsive. And then after I'm done, I have to make sure that in case of an emergency, the emergency shuttle valve closes in under 200 milliseconds. So typically I would command 100% and physically go to the valve and disconnect the command cable. And the emergency shut valve is usually a spring-loaded valve, what we call fail-safe close. So once you pull out the cable, it should close within the 200 millisecond test. And this usually is done to ensure that we do not have any introduction of gas into the system when we have an emergency situation and need to shut down. This is an example of an outage of a turbine that was built in 1975. This is the VF93. And you can see clearly the air intake, you needed actually a ladder to be able to access. And there are no variable inlet guide vanes. So it means that a part of the compressor already is embedded in your air intake manifold. And this concrete building is actually the air intake housing. So the air is sucked in through the concrete underneath into a sort of a manifold that allows the air to go into the compressor. So in this particular instance, there was no IGV. The work was much simpler, but also it means that when you had issues in terms of emission requirements, you had even no possibility or to introduce a degree of control. Now, this is an example of how the setup looked like before the introduction of the double block and bleed norm. So what happens is, if I want to work on this system, I just have to crack open this locking nut. I walk away 15 minutes, I come back again, and I use a gas detector to ensure I don't have any gas here before I proceed to fully open this tapping point, which goes to the manometer. And then I can disassemble the ESV and send it off for calibration. So some of the typical challenges that I encounter nowadays are outdated norms or machines that are so old that the typical control design doesn't apply to. And you always have to be extra cautious because you don't want to be that famous engineer who is known for blowing up something. So you have to really make sure your risk assessment is in place. You need maybe a little extra time to perform your duties, but at the end of the day, you want to be able to complete your job and go back home. Now, what are some of the other challenges that I've come across? Lack of spare parts. We know this all too well. Case in point, Afam Power Plant in Port Harcourt. I remember 11 years ago, I was invited after a fire incident, and because of the lack of parts, even from the OEM, because what the OEMs are doing nowadays is introducing newer components that they can supply, which means that they force, let's say, owners of gas turbines to drift away from old DCS. It's a way to generate revenue for the company. However, if you do face some difficulties and you cannot get specific speed probes, you have to fix what you have. And the people, the knowledge is very scarce nowadays, and also the parts are very difficult to come by. And because the gas turbines are normed, or they have certain norms that they have to fulfill, you cannot just use any part. You have to make sure that it's certified. You want to have your license to operate in case you do have a disaster. You want your insurance to pay. So all these underwriters want to make sure that at least you are running the unit in such a way that is compliant with the norms in place. Now, another challenge we see is cost cutting. The OEMs are under a lot of pressure to optimize the system so that it becomes cheaper for the client, also to be able to compete with others who are in the business. And you will realize that you cannot be too comfortable with your knowledge, because as the years go by, certain systems are just replaced. Case in point is when I went to Bahrain and I realized that they had scrapped the controller completely and outsourced part of it into a different module. So I also had to sit down and read a little bit before I knew what was different. Now, it's not always that easy. When you start a gas turbine, certain things could be amiss, and you might need to balance the turbine. And then we have to connect what we call the LVMS equipment. This is a pellet case with a computer and a screen that allows us to collect all the vibrations from the bearings into this system with a remote connection to our partners who are going to be able to give us recommendations on how best to balance the turbine. They will tell us where to introduce weights in which bearings or where to take some out. Additionally, there is also the ability to collect combustion data from the Argo system, which is literally a spectrum analysis of the combustion process. So here you have your humming flange measurements, which is the pressure drop over your 24 burners. And then you have accelerometers that also pick up combustion dynamics that cause the ceramic shields within the combustion chamber to shake. And if you do have these Gs over a certain amount, automatically you have to shut down and inspect, because you could have parts breaking off and coming loose in your turbine. So what does a successful completion of the job look like for me? When I start, I want to be able, in this case, you can see there is a purge cycle. So the purge cycle, you operate your generator as a motor, where you introduce current to turn the rotor, and you do that to allow a certain amount of air through the whole system, compressor, chamber, and turbine, because you want to make sure there are no explosive gases trapped in the system. This is actually a safety requirement, and if you have a boiler, your purge time is usually much longer than if you have an open cycle, okay? Now, if you are successful, you should see an increase in temperature, pretty steep, and then it should drop when your bleed valves close, and then remain more or less constant. Reason is different parts of the turbine heat up differently, and you want them to be as uniform as possible to reduce your vibrations on the system. Once that is complete, the synchronization process will occur here. This is the light blue line. And then you would go up in steps until your switchover point, where depending on the type of turbine, whether it's a 94.2 or 94.3, your ball valves activate or you close the diffusion, you open the premix, and then you go up in load again until you hit your base load. You do your heat soaking, and then you come back down again and you switch over at this point. So this would be, let's say, from start to finish, 10 hours, where you take the data that you require for your analysis to make sure that the unit is up and running, your vibrations are all okay, and you release the machine for commercial operation. Now, what are some of the future trends? I talked a little bit about cost cutting, and you can see in this particular scenario, this is your PS, your power supply. This would be your automation processor, your AP. This would be your CP, your communication processor. So this whole setup is on the left is one channel, and then you have a redundant system. So this will be your second channel. In the past, there was a module here called the FM458, and this has now been taken out. It means this module is no longer required. It cuts the costs, and the profit margins grow. What did they do with the functions that are processed here? They outsourced them into the ADFEM module. So the ADFEM module is a module that takes in very fast signals like speed and valve positions, and they've incorporated some microcontrollers there as well, with the ability to perform certain tasks in order to relieve the automation processor. This device you see here is a flight recorder. This is no longer necessary. It is more or less optional. So some clients who do not want to procure it, they go without it. And you can see, as usual, you have a Profi signal connection on one channel, which comes into the master rack. And then you have a second one that goes to your slave rack. So whatever the master performs, the slave is doing the exact same thing. And in case this one fails, the master fails, there is an automatic bumpless switchover onto the slave system. Yeah. Now, you can also see what was done for the main controller has also been done for the protection system. So you do not have your classic 95F, 95U protection systems. They are now outsourced, and they outsource into the Brown modules. So now this Brown module has the capability not only to measure the speed of the turbine. So you see, again, channel A and channel B to each module. So you have 3 for the speed measurements and 3 for the protection. So it means now you have the whole protection system, which used to be a whole cabinet, being compacted into one rack. And this is the way forward. Systems are being put together, being compacted in order to reduce cost of production and increase margin, profit margins. And then you see there is, this picture is actually of the Argos OMDS. It no longer comes with a screen. The screens are connected via cables into the main control room. So the real estate here is also made smaller. And then over here you have for your IGV, your 2, we call them cubular. They are opto elements that usually take a certain amount of pulses to determine the angle of a transducer. So you have for the IGV, you have 2. For the VGV first stage, you have 2, and for the VGV second stage, you have an additional 2. And all the systems are redundant. So in case of loss of master, there's an automatic switchover. Now, future trends. A lot of customers want to increase the availability of gas turbines. It means they want to have the downtime as little as possible. And one step that is booming right now is the introduction of remote monitoring systems. It means we are trying to figure out how best we can access and analyze real-time data from the gas turbines, process them such that we can give recommendations to the client to tell them, hey, based on your combustion dynamics, we've realized that your gas quality has changed. Can you please verify that? If the client says, well, everything is okay with my gas supplier, my gas chromatography is okay, then we would have to maybe introduce a tuning session where we come on site to make sure we fine-tune the machine to be able to run in a safe environment based on the current gas characteristics that we have. Or there could be weather changes, it could go cold or hot for whatever reason, and you automatically move a little bit out of your optimal zone, requiring an external tuning session. So this is, let's say, the trend, because a lot of customers want to keep running their gas turbines for years. Some of them are, the oldest gas turbine I've been on was built in 1973, and it's still operational. So as you can see, the 84 years gas turbine history is set to grow. So with that, I'm at the end of my presentation. This is a little picture I took last year in AFAM during the refurbishment of GT20. So if you have any questions, please feel free to ask them.
Thank you so much, Engineer Frank, for your presentation. Can you all hear me? Can you hear me?
Yes, we can. Yes.
So, yeah, so thank you so much, Engineer Frank, for that presentation. That's quite interesting. I believe that there'll be quite a number of engineers on this webinar who are in the power sector and are very conversant with gas turbines. So I would expect some interactions. However, I would say that if you want to ask questions, you can just raise your hands and then we will come to you, or you can type your question in the chat section and then we will also come to you. So before the questions start coming, let me just ask a quick question, Engineer Frank. When you were talking about the type of challenges on the VF93, you talked about how air, is being taken from the underground concrete through a manifold into the compressor. How is that air being purified to the level that the compressor requires?
Not at all. I mean, some of them just have a bed screen in front. They don't even have filters installed. It means in winter, if they do need to run, they have to have either how do you call them, glycol going through pipes to make sure that they don't have any ice forming, because the ice going through the compressor will actually damage it. So these systems are so old that apart from a bed screen, there's really nothing in there. So every time there is an outage, manually we have to try and clean the IGVs because they get very dirty.
Okay. Okay, so it's like a manual operation to ensure the air gets into the compressor.
Yes. With newer systems, you have a pre-filter, a main filter, and a fine filter. So you have 3 stages. So depending on where you are, if you are in a very cold region, you would usually have your air preheating systems when the temperature drops below 8 degrees to prevent the formation of ice in the compressor. If you are in a warm climate where you really need more power, what you have is evaporative coolers or air fogging systems or wet compression, where you inject water either in the compressor inlet or directly through the burner to increase your demand, your mass flow and demand.
Okay. Okay, thank you so much. So go quickly to the question. I've got Yusuf Israel. Your hand is up. Please ask your question. Go straight to the point. You can unmute yourself.
All right, thank you very much. I want to thank the host and the presenter. So my question is this: what will you advise someone who wants to invest in gas turbines for the purpose of generating electricity? Let me elaborate. I'm working in the oil and gas sector. So we are looking at owning the technology that refines gas, because Nigeria is more of a gas country than even crude oil. So we want to channel some of this gas to the generation of electricity. So what will you advise somebody like me who wants to invest in gas turbines for the purpose of generating electricity in Nigeria? Thank you.
Thank you for the question. With regards to Nigeria, I would not recommend anything with too much of an electrical output. Reason being, you do have situations where your gas turbine goes down. So are you able to, let's say, stem a 300 megawatt loss if your unit goes into an outage? I would rather recommend smaller units. You could have maybe 140 megawatts as a main as a base load machine, and then smaller ones that can take over the load in case one of your units goes out into an outage. But to give you that flexibility, because like they say, in the land of the blind, the one eye is king. So if you do have 3 or 4 machines that are generating 280 megawatt, if you lose one, 3 are still generating, you have 210. It's still better than nothing. So I would personally go for systems that are not too sophisticated, that are robust, and that do not have, let's say, too much of an electrical output. What we would say an E-class machine. Yeah, they are having years of proven experience. If you want to go with Siemens, you would have the V94.2. If you want to go with GE, you would have the frame 9s. If you want to go with Alstoms, you have the 13E2s. So these are the kind of turbines I'll be looking at, because the return on investment is actually quite short. The maintenance is easy. You can have extended lifetime cycles, and you have a lot of manufacturers who are able to provide spares. Case in point, Sulzer, they are able to refurbish also the parts for you. So if you settle for an E-class, you should be on a good way.
Thank you so much. Thank you so much, Engineer Frank, for that response. We'll go quickly to our own secretary, Simon. Please go ahead with your question, straight to the question, please. Thank you. You can unmute yourself.
All right, thank you very much, Engineer Shagun. Yeah, Engineer Frank, thank you so much for a good presentation. I'll just go straight to my questions. Number one, we know they have different OEMs that produce gas turbines. What then do we do as practicing engineers for maintenance, or how is the industry putting up with integration and inclusion based on the fact that these companies all have their own special designs or little differences in equipment, and you might want to scale up or you want to integrate. How do we then be able to include all the different types of gas turbines to the system to be able to have an effective maintenance output? That's one. Then second question, when you talk about, we're talking about the valve validation. Do you use the SVCs to do that, or you do them manually using your hands to check them one or the other, or how do you really handle that process?
Okay, thank you too. To answer maybe the second question, this is specific to the DCS. So if you have T3000 version 9 ongoing, you have to do the calibration within the DCS. There's a specific block in the logic. With regards to HART, I'm not familiar. I think you're talking about industrial turbines. They might have what you call the MOOC controller, or like with GE, they have the LVDTs. So you might need external equipment to do that. But typically, with these ones, you do it with the system, the DCS system. And with regards to your first question, unfortunately, there's no standard. If you are a young engineer, I can understand the task at hand can be very daunting. Your only way is by, you learn how to swim in a pool or in the sea. You cannot read textbooks and become a good swimmer. And unfortunately, it's not good news, but as a starting engineer, you really have to go through fire, and then you become what you are. There's no simple way. It's rather unfortunate.
Thank you so much for that response. You go through fire.
Yeah.
You get strong. Anyway, next question, Engineer Ikechukwu. You have your hands raised up. If you want to go ahead with your question, unmute yourself. Engineer Ikechukwu Monday. Okay, I'll go to the next person, Samuel Tochi. You have your hands raised up. Please unmute yourself and ask your question.
Sorry. I was trying to unmute.
All right. Okay.
Good evening, everybody.
Good evening. Nice to have you here.
Thank you very much. Frank, for mine is just a comment, Just want to, thank Frank for making our time to present this wonderful and fantastic presentation, So I'm so glad that you were able to put this and pass this fantastic knowledge. So thank you very much. And also to the team for getting this done. Yeah, I'm on transit, so I'm not fully involved, but I joined to just listen in. So thank you for the great job the branch is doing, the chairman and members of the ESCO and every member. So thank you very much.
Thank you so much for that, Engineer Ikechukwu Monday. Samuel Tochi, please go ahead with your question. You can unmute yourself. Samuel Tochi.
Good evening, everyone.
Good evening.
And okay, that was a wonderful presentation from you, Mr. Frank. So my question is this: though I don't have any background or much background in this aspect of engineering. But then I'm wondering if you can throw more light on this. I understand that gas is costlier than all other or fluid or all other components, or let me say, okay, I understand we have water turbine, steam turbine, and wind turbine. All these use natural or cheaper, would I call it fluid or gas? However, the topic is on gas turbines. So knowing that gas is costlier than other means of designing turbine, and then again, I understand that the efficiency of gas turbine is actually lower than that of steam turbine or water turbine. Is there really any advantage, or what are the major reasons why someone should consider gas turbine over water or steam turbine, that the traditional way of generating electricity?
Thank you
I
so
don't
much.
know if my question is clear.
I think I understand your question. I'm trying to figure out how best I can answer it. I mean, largely, gas turbines are like, let's say, the backbone of the industry. Why do I say that? You typically, when you talk about industrialized nations, country in point, Germany is known for its steel export. And the steel industry is a very heavy user of electricity, especially of cheap electricity. And up until recently, coal was the main source. Now, with all the attention given to global climate concerns, we definitely have to wean ourselves off and go into renewable. But this renewable transformation is not going to happen overnight. You still need to have a strong economy. At the same time, you need to innovate. So gas turbines are actually right now not being used as base load machines anymore, like in South Africa. They are being used to cover the peak demand. So in the morning, when people wake up, turn on their kettles, prepare to go to work, then that peak demand is covered by the gas turbines. And then you have your renewables or your base load machines like coal turbines running constantly. But those peaks in the system are covered by gas turbines. At the moment, there are, let me say, efforts underway to try and use alternative systems. You have battery packs that buy energy when it's cheap, store it, and when the demand is high and there's a peak, they compensate. You also have solar coming in, you have geothermal, you have tidal. All these things are based on or subject to availability. I mean, if you're in Abuja, obviously you can't use tidal energy. And if you are, let's say, in the south of Germany, you cannot use wind energy. But the gas turbines are also innovating. We have actually projects where hydrogen is dissolved into diesel or oil, actually, for the lack of a better medium. So waste oil from the industry, for example, from kitchens are recycled, and hydrogen is added 10-15% and is introduced into a gas turbine, and it works. It burns perfectly. What you're looking for is you're breaking the carbon-hydrogen bonds and taking the energy released out. So whether you are burning ethanol or biodiesel or whatever it is, you need to make sure that your net energy is positive. Then you are on the winning side. However, there are also side effects. When you introduce hydrogen into oil, you have something called fatty acid methyl esters, and these are corrosive byproducts that can attack your piping. So if you are not careful, you would sacrifice the seals of your ball valves, you will damage components within your valves. So you see that there is an innovation process going on right now. For gas turbines to still be around in 50 years, they need to innovate. On the other hand, there are several other options. We have also biomass plants that are actually boiling water with waste that is being heated, and you have to make sure that you clean the flue gases before you leave them into the environment. So this challenge that we have right now, we have to learn to wean ourselves off fossil fuel, because eventually we'll exhaust everything, and we have to look for newer ways of funding our industry and living as a society. So gas turbines are an option. In terms of price, you said it's quite expensive. In Europe, gas is still cheaper than oil. So if you are running on oil, it's expensive. Unless, of course, you go to crude oil, then it becomes cheap again. But with crude oil, you have byproducts, sulfur oxides, and all these things that you have to take into consideration. Also, I must highlight that there are differences in gas quality. The gas in Nigeria is very different from the gas in Bahrain, because the gas in Bahrain is known as kuf gas. It has certain substances in there that have to be taken out, and then the gas density is different. It burns very different to the machines in Nigeria. So that is why you can have two identical machines in two different countries, and they behave completely differently. So this is also one thing. I mean, gas is still relatively cheap, but the question is its availability. You know, that is what I see as a challenge.
Thank you so much, Engineer Frank, for that. We've got two hands raised up. We will quickly take them and then take two questions from the comments, and that will be all for the webinar. I know there are so many people itching to ask questions, but because of the constraint of time, we'll just limit it to the two hands raised and the two questions in the chat. So I will respectfully call Engineer Ademola Agoro to please unmute yourself and ask your question.
Okay, thank you. I want to just go straight to the question. I want to thank the presenter, though I joined a bit late, but I listened attentively to what you've said, and it shows that if you are very knowledgeable in this field. But my question, I was worried when you said something that there's no standard. Because I cannot remember the person that asked the question I was asked, because as an engineer, the basic thing for us is the first principle. Once you understand the basic standard behind any technology, whether it's from GE, it's from Aston, it's from Siemens, that is the only way that can help to be able to do re-engineering. But like you said, there's a lot of new things that are coming every day. You are able to tell us that even when you travel to Bahrain, you discover, and you are able. It's because I just want to find out. Is it that there is no in the development of a gas turbine? Is there no basic principle that one needs to follow? If it is, what is it? But if not, how do you get to the process of doing the re-engineering? And another second question of mine is the issue of this CNG, because it's obvious today, especially in Nigeria, many people just talking about converting into CNG. Many people, which you rarely explain in some. I was in Italy last week, and some of these things that you are saying about ethanol, hydrogen, was I explained because the NSC is trying to do a kind of a collaboration with some Italian company. Most of those things were explained. I think if you have, I don't know whether you have expertise in some of this area. Thank you.
Thank you for the question. With regards to the standardization, yes, I mean, the underlying principle is thermodynamics. If you are able to harness the greatest area underneath the thermodynamic curve, you have the biggest energy that you've generated. So that is how come you have sequential combustion chambers, where rather than heat the gas turbine exhaust to as high a temperature as possible, they prefer to inject that waste gas as a input gas for the next turbine. But it comes with its set of challenges. I think the question was along the lines for new engineers starting, is there a standardization in terms of a way to go about learning across all the different OEMs? Because they feel that having to learn first Siemens OEM operation concept, having to learn that of GE, having to learn that of Mitsubishi, yeah, they might be similar, or you might have some subtle differences between radial compressors and axial compressors. But unfortunately, you have to really spend the time and effort to know each and every system that you're working with. That was with regards to the first question. It was the second part of your question, which I didn't, with regards to hydrogen, whether I think that is the way forward. Well, is that the question you asked?
No.
About CNG.
No, it's about CNG.
CNG.
Yes, because for me, I'm an electrical engineer. I didn't even know that LNG is better than CNG. The only thing I just hear in Nigeria is that convert CNG to this, but when the guy explained, and I know we have a lot of LNG in Nigeria, we have CNG, but even the technology behind it, which you explained, I was just saying that I didn't even know that. But when I was in Italy, I knew that you can use ethanol. I saw a generator that is powered by ethanol. So there's a lot to this your gas that I think you need to help us with.
With regard to the different types of gases, I'm not also very conversant, but I know that we usually have a chromatography device that tells us a lot about the gas we're using in terms of its calorific value and some of the composition, because we have to, for the control system, we have to take certain things into consideration, like the density of the gas and the calorific value, because it will determine how I pre-position my control valves. If I position them too wide, I would have an explosion. If I position them too low, I will not have the demand required. So with that, we rely on the input from gas chromatography devices, and I would not really know everything upstream of that point. In terms of, what was the other part of the question?
I think that may just be the question about CNG, the use and the conversion. So maybe that's the response, if I would say.
Yeah, I really don't have more information with regards to that, except for what we need for the control system.
Okay, no problem. Thank you so much for that. We'll take a question from Dennis Dania. Please make it quick because we are pushed for time, and I will take the 2 questions in the comment section. So Dennis, please unmute yourself and ask your question. Is Dennis there? Okay, I will just go to the question in the comment section. So can you briefly discuss the challenges and solutions related to turbine overspeed protection systems in power generation application? Challenges and solutions of overspeed.
Yes, quickly, overspeed, you have 2 ways of doing it. You either do a live overspeed, where you physically accelerate the rotor into the limit and you trip the unit. That is what the Alstom turbines typically do or used to do. How Siemens does it is they simulate a lower frequency and activate the individual channels. Both of them actually work the same way in terms of they issue the trip signal during a startup. And there's really no advantage or disadvantage. I mean, if you really do have a problem and you do the live overspeed test, the worst case is you could damage the equipment. So if it's not required by law or by insurance company to demonstrate it, you'd always fall back to a simulation where you activate the individual channels, trip the unit, and demonstrate that the protection of the system is guaranteed in the case of an overspeed scenario.
Okay, thank you so much for that. The second question is on the comment section, I think from Agbo Mary, is you mentioned that the flame is adjusted to keep emission within a certain level. What's the emission requirement? That is saying, is the emission requirements the same for all gas turbines?
If you buy a gas turbine from Europe, then yes, the emission requirements are pretty standard. However, you can have certain countries enforce them more strictly than others. Typically, when we talk about the V94.3, we have 15 ppm that we try and hit as a target, or 30 milligrams per norm cubic meters. In the past, it used to be 60-30. Now it's becoming tighter. The emission requirements are being monitored. For the old machines, there are some exceptions. Those that were built before a certain time are still allowed to run with the higher limits, but the newer ones have to comply. So then additional systems come in, like purge water system, in order to create an emulsion to reduce the effects of the NOxes and all that. Or you can have a post-gas treatment where you have ammonia introduced to capture some of the NOx. So there are different systems in place. But to answer the questions, every country has its own rule. As time goes by, we see that the limit gets reduced in order to make sure that the pollution levels are held in check.
Okay, thank you so much. And our last question will be from Ibrahim Achineje. Sorry if I didn't pronounce your name correctly. Can you unmute and ask your question? We're pushed for time, so please go straight to the point. Thank you, sir.
It's okay. Can you hear me?
Yes, we can.
Right, good. So some really good and interesting discussions there. So mine is more around where the world is going in terms of climate change. And one of that essentially is transitioning to cleaner energy. And I believe hydrogen is a favored candidate. So as we do know, currently gas turbines, they use natural gas as the fuel. If we are to move to nitrogen, what sort of changes would be required on existing gas turbines, right, that can maintain the same level of power and also meet emission requirements? Do we expect a significant retrofit? Say, for example, the combustion chamber, the control valves, and other components, or would you expect a minor change? It's just something I'm not really.
The changes are subtle. However, what we have to still wait for is the long-term effects. Like I said, there are pilot projects underway. I think GE right now have successfully managed to introduce, is it 25% in their test F-class machine in the Netherlands, Flevoland. I know Unipat did that with 10%, where they introduced hydrogen into the oil. But like I said, when you dissolve hydrogen in oil, you end up having fatty acid methyl esters buildup. So if you have a plant that runs on oil once a year, you'll have an accumulation of an acidic oil in your piping. So long-term effects such as corrosion on your pipes, we still have to wait and see how it pans out. Obviously, there could be measures taken to coat, let's say, the inner parts of the pipe, but then it will come at an increased cost. So the client would have to decide whether retrofitting the existing system to run on alternative fuel sources or let me say products merits the benefit that they stand to get out of it. But it's an ongoing process. This year alone, I've been to Flevoland, and I think last year I was in Unipa, where those test pilots were done. Eventually, you will have the ability to run with 80%, I believe. But as it stands now, I don't know the impact it will have long term.
Right. Thank you.
Thank you so much, Engineer Frank. Thank you, everybody. Apologies for the questions that we're not able to take within the time. But if you can drop them, we can pass them to Engineer Frank and provide you response. So before I hand over to the branch chairman, I want to really thank you so much, Engineer Frank, for your time. I know you're quite a busy man flying from one gas turbine to the other, but you made time to attend. I will also use this opportunity to also announce that our next webinar will be in November, and it's going to be an interesting one for all of us, and particularly for those in the construction industry, building services. It's about premature collapse and fire-rated containments for cable. It's going to be, the presentation will be by Legrand, and it's going to be a CPD one. So there's going to be a CPD certificate that will be issued, which will be a contribution to your yearly CPD hours. So if you can put it in your time, we will obviously let you know when the dates and time is, but it will be an interesting one.